Hello friends, in dynamic recrystallization there is another topic we are taking today and it is going to be called as continuous dynamic recrystallization and geometric dynamic recrystallization. Okay. So, if you remember the previous two lectures were related to the discontinuous dynamic recrystallization, okay. And as I told you in that the discontinuous dynamic recrystallization is the nucleation of a strain free grain and the growth of a strain free grain. Okay. So, when you have this kind of process, it is called discontinuous dynamic recrystallization. Okay. Then the new terms which have come in dynamic recrystallization is because people have observed some new microstructural behavior, okay, and from there they have said that it is now a different type of recrystallization process, and that is why a new name is called continuous dynamic recrystallization and another one is geometric dynamic recrystallization. Okay, so the continuous dynamic recrystallization actually is very similar to a dynamic recovery type of process. Okay, so in dynamic recovery also we have seen that the material with high stacking fault energy are predominantly they restore their mechanical property through dynamic recovery. Okay. And in continuous dynamic recrystallization also high stacking fault energy materials are the one which are predominantly get recrystallized through this particular process. As I told you that dynamic recovery kind of recovery is a dominant process, and because of that some people also refer to it as an extended recovery process. Means if you take recovery to even larger strain, okay, maybe it will come as a recrystallization process. Okay. So, just to kind of differentiate between recrystallization and recovery, okay, recrystallization means I should have predominantly high angle grain boundary. That means most of the grains should be surrounded by high angle grain boundary, whereas in a recovered grain, okay, there are large grains and within that you have sub grains, and these sub grains are predominantly surrounded by a low angle grain boundary. Okay. So, recrystallization means I should have finer grains, whereas recovery means I can have finer sub grains. Okay. So, this kind of classification should be clear in your mind. Why this kind of process takes place especially in high stacking fault energy material? Because recovery is very efficient. Okay. Now, when the recovery is very efficient means dislocation can easily recover. Okay. I cannot have a discontinuous dynamic recrystallization which requires certain amount of dislocation density. Okay. So, now to have a recrystallization process, I need higher strain to exhibit recrystallized microstructure in case of continuous dynamic recrystallization. Okay. So, you can say at lower strain you will see the microstructure as a dynamically recovered microstructure, but if you go to higher strains, okay, you will start seeing recrystallization taking place. Now, why it was not earlier kind of identified? Okay, because in our conventional thermomechanical processes, for example, rolling or extrusion or forging, okay, which are based on the compression cycle. Okay. In compression you can always understand that there will be induced tensile stresses also. So, when you apply very large compressive strain, okay, there will be large tensile strain also. Okay. And because of that, because you have to maintain constant volume, okay, because of that you will ultimately have cracking in the material. So, material will crack if I apply very high compressive strains. Okay. So, I cannot apply very high compressive strain in normal conventional thermomechanical processing, and that is why maybe people have not observed CDRX before. But when the severe plastic deformation processes come into vogue, okay, so for example, you might have heard about equichannel angular pressing ECAP or high pressure torsion HPT, okay, or friction stir processing FSP. Okay. There are a large number of processes are there in this category, The strain in these cases is usually through shear process. Okay. So, shear strain is imposed, these are not compressive strain based processes. So, the deformation is through shear, okay. And because of that you are able to impart large amount of strain during these processes, and because of that you are able to see this CDRX process in these severe plastic deformation process. Okay. Another area or another deformation where you can see this continuous dynamic recrystallization is the superplastic deformation. Okay. I will tell you what do we mean by superplastic deformation in a very small section is there. Okay. So, because in superplastic deformation also you have very high strains you can achieve. So, the CDRX processes people have seen in during superplastic deformation. Now, what are the characteristics of continuous dynamic recrystallization? As we have already seen in discontinuous dynamic recrystallization, you have nucleation and growth mechanism, whereas in this case of course there is no nucleation and growth separate as mechanism. Okay. In fact, in this you have progressive evolution of microstructure. Okay. So, it is a continuous kind of process where grain boundaries are converting from low angle to high angle. Okay. So, basically low angle grain boundary kind of transform into high angle grain boundary. Okay. And there are different mechanisms people have proposed that how this can happen as a function of strain. So, as a function of strain, low angle high angle boundary convert into high angle grain boundary. So, in dynamic recovery, as I was telling you that you have big grains, okay, and they have small sub grains. Okay. So, this I can kind of make it bold to show that these are high angle grain boundaries, and within that you have sub grain boundaries and so on. Okay. Maybe not correctly drawn here. Okay. So, now these subgrain boundaries, these are all low angle grain boundaries, and these will in the process will convert into high angle grain boundary through continuous strain, large amount of strain. And as we have seen in dynamic recovery, stress increases with strain, and at large strains a steady state stress is reached with which increases with increase in Z. Okay. So, if you see the flow stress curve in this process, okay, it will be like what you see in dynamic recovery, it will have a steady state condition. Okay. And with increase in Z, okay, you will have higher stresses. Okay. So, I can have multiple curves like this. So, in this direction your Z is increasing. Okay. For example, this is what I was telling you about superplasticity. Okay. So, this is a very old paper in 1992 CDRX in superplastic aluminum, lithium, copper, magnesium and zirconium alloy. Okay. This is aluminum lithium 8090 alloy, and basically superplasticity is very high elongation, more than 300% at low strain rate and temperature of more than 0.4 Tm. So, the conditions are typical of any recovery recrystallization process, okay, high temperature. However, the strain rates are low in case of superplasticity as compared to other conventional or SPD processes. However, the elongation is very high, you can achieve elongation of 1000% and even more than that. Okay. So, there in their work they showed that as a function of true strain, okay, so average misorientation of the whole microstructure is changing as a function of strain. Okay. So, initially the microstructure has, because average misorientation is low, that means it might have high angle grain boundary and low angle grain boundary, but if you combine all and take average of that, okay, it is very low, less than even 5 degree. That means predominantly the material has low angle grain boundaries. Okay. So, these are means already subgrains are there and so on. Okay. And as the deformation is progressing, okay, you can see that the slowly the average misorientation is increasing, okay, and reaching some steady state kind of condition at around 20 degree or so. Okay. So, average misorientation, and it is not a sharp change from one average misorientation to another one, but it is a gradual change in the misorientation, average misorientation in the microstructure with the strain. And these two curves, one you can see the bold one is at 10 to the power minus 3, whereas the dotted one is at 10 to the power minus 4. Okay. So, another interesting thing is that at lower strain rate you can achieve the kinetics of change in the microstructure is higher. Okay. So, at lower strain rate you can not exactly kinetic, but at lower strain I would say that at lower strain you are able to get the high angle grain boundaries, more high angle grain boundaries at lower strain rate. I think I have mentioned that in the slide also, the earlier slide. No, okay. Anyway, so the strain rate, the effect of a strain rate is as you go to lower strain rate, at lower value of strain you are able to achieve very high average misorientation. Okay. So, around 17 degree or so you are able to achieve at around 0.4 strain, whereas in case of higher strain rate condition almost strain of 1 is required to achieve that kind of average misorientation. Okay. Now, how the CDRX actually takes place? It is gradual increase in misorientation of low angle grain boundaries, okay, as we have just discussed. Okay. And to kind of remove all the other effects of grain boundaries and so on, okay, there is some work on the single crystal of pure aluminum was done. Okay. And there people have seen that, okay, the microstructure initially is getting divided into sub grains, okay, and that is slowly converting into high angle grain boundaries. Okay. So, a single crystal now is dividing into some low angle grain boundary areas. Okay. So, this dotted one is even less than 1 degree, the lighter ones are 1 to 6 degree, okay. Slightly darker ones are 6 to 15 degree, and very bold ones are the 15 to 30 degree. Okay. So, they are able to show that how the microstructure is evolving through deformation in a single crystal. Okay. So, how it takes place is that initial deformation give rise to formation of subgrains. So, initial deformation when you are giving, okay, so through recovery, dynamic recovery processes, the subgrains form, okay, and these subgrains are of course surrounded by low angle grain boundaries. Okay. And later these subgrain boundaries or low angle grain boundaries are there is a progressive accumulation of dislocation in this low angle grain boundaries. So, dislocation recovery is continuously going on. Okay. So, all these subgrains which are formed, okay. So, because of the recovery process, continuous recovery, you are continuously deforming and there is a continuous recovery of dislocation. These low angle grain boundaries are progressively changing from low angle grain boundary to high angle grain boundary. Okay. So, progressive accumulation of dislocation into LAGBs, low angle grain boundaries, increase their misorientation, and eventually high angle grain boundaries are formed. Okay. When the misorientation angle reaches a critical value of more than 15 degree. So, in general around 15 degree is what we take as the demarcation between a low angle and high angle grain boundary. Okay. So, the continuous recovery of this dislocation changes the low angle grain boundary to high angle grain boundaries. Another mechanism which is proposed for this CDRX process, okay, is through lattice rotation, okay, and that is actually more visible in magnesium alloys or solute containing aluminum magnesium alloys. Okay. So, magnesium has a good solubility in aluminum. Okay. So, the magnesium alloys, because it has a hexagonal closed pack structure, okay, and because it has HCP structure, the slip system are only, there are only 3 slip system, okay, out of which only 2 are independent. Okay. So, you do not satisfy the Taylor criterion of 5 independent slip system in HCP materials. Okay. So, you have less than 5 slip system in case of magnesium alloys, okay, and because of that you have predominantly dislocation only in one plane. Okay. Because of that, when the dislocation accumulate, okay, you can see that there are on the pre-existing grain boundary, okay, this dislocation are coming and they are accumulating, and because of that you have this kind of grain rotation. Okay. So, there is a lattice rotation because of the very high amount of dislocation density in the vicinity of the grain boundary. Okay. And another nice micrograph is shown here also. So, this must be some prior grain boundary, and around that you have this small grains which have nucleated through lattice rotation. Okay. So, this lattice rotation give rise to this kind of dislocation at the grain boundary. Okay. So, this is usually you will see in magnesium alloys or aluminum magnesium alloys, okay, when you deform to very high strains obviously. Another example is the CDRX in your AZ31 magnesium alloy. Okay. So, this is also a magnesium alloy, where they have tried to show that how the grain boundaries are getting converted. So, this grain boundary B here, which is shown with a white color. So, white ones are the low angle grain boundary and the dark black ones are the high angle grain boundary. There is another grain boundary C, okay, at here, okay, again a low angle grain boundary. So, what they are trying to say that these small grains which have formed at the grain boundaries is through change in the misorientation of this low angle grain boundary. So, earlier this also must have been a low angle grain boundary, but continuous deformation, okay, converts this now low angle grain boundary into high angle grain boundary. So, if we keep deforming, okay, later on you will see that this B boundary here and C boundary here, okay, both will convert from low angle, which is shown with the white color right now, into a high angle grain boundary. Okay. And the reason for that, to give this kind of argument, is that if you kind of plot that how the misorientation is changing within the grain. Okay. So, this if you see this curve, okay, this is misorientation on y axis, this is distance, and we are starting from A here, okay, and going from A towards the grain boundary. So, if you see the misorientation development, okay. So, in the interior of the grain up to some distance, you will see that there is hardly any misorientation development. What does it mean? That the dislocation density here is low, okay, dislocation density is low here, okay, in the interior of the grain, and as you are going towards the grain boundary, there is large number of dislocation density, as well as there may be some subgrain boundaries are forming or very low angle grain boundary are forming, okay, and that is giving rise to this misorientation development as you go from point A towards the grain boundary. Okay. So, this misorientation development is, as I am telling you, that it will be because of the dislocation density. So, you have high dislocation density very close to the grain boundary. So, this dislocation will now, as you can see, will be getting absorbed in this low angle grain boundary of B and C, okay, and this will be converting into high angle grain boundary as the deformation progresses. Okay. So, another way of looking at how the continuous dynamic recrystallization takes place in the material. Okay. The next type of dynamic recrystallization. So, we have seen till now discontinuous dynamic recrystallization, continuous dynamic recrystallization, and this is another one which is called geometric dynamic recrystallization. This is mainly observed for materials with again high staking fault energy. Okay. So, in fact, some people are categorizing GDRX also within CDRX. So, it is considered as a part of the continuous dynamic recrystallization, and of course, it will be also at elevated temperature at low strain rates and large strains. So, mainly all these conditions are also you will find in CDRX. So, only how the recrystallization process takes place or what is the mechanism, that is different than the CDRX process. So, subgrains are formed as usual after a critical deformation, first near original high angle grain boundaries. So, around high angle grain boundaries, because that is where you have more dislocation density. So, near that subgrains will form. The subgrain boundaries, the misorientation of the subgrain boundaries is not usually, is very small, actually is not usually more than 2 degree or around 2 degree basically. And because of that you will see a very bimodal distribution of misorientation angle during GDRX. So, if I plot frequency here and misorientation, or let me write misorientation here on the x axis, okay, you will see some curve like this, okay, a bimodal. Okay. If it is so predominantly low angle grain boundary and predominantly high angle grain boundaries, only two type of grain boundary misorientation will be frequency will be very high, and texture largely remain unchanged during GDRX process, whereas in DDRX you have a big change in the in the texture of the recrystallized microstructure. Now, what is the mechanism? So, the migration of high angle grain boundary, okay, they migrate to form serrations in the high angle grain boundary. I will show you a schematic for that. What do we mean by these serrations? The serrations are developed during hot deformation by DRV with a wavelength similar to subgrain size. So, as we have just seen that the subgrains will be forming at the vicinity of the high angle grain boundary. Okay. So, they form serrations, okay, and this wavelength of the serration is equal to the size of the subgrains. Okay. And when you, and of course, as we have already seen, we have to apply very large strain. Okay. So, when it is kind of a flattening of the grain process. Okay. So, if you start with the equiax grain, okay, progressively it will become more and more flat kind of grain. Okay. And of course, it will have this kind of serrations in the grain boundary, and the wavelength will be equal to the subgrain size. So, grain thinning will takes place, okay, with significant grain elongation. Okay. And when they are getting thinned, okay, what will happen is that these two high angle grain boundary, okay, let me kind of exaggerate it. So, basically you have wavelength. So, it keeps getting smaller and smaller. Okay. So, what will happen, you have a subgrain here and subgrain here, and this is my high angle grain boundary. Okay. And if you keep deforming it, what will happen, this will impinge with each other. Okay. Or also I would call it as a pinching off. Okay. You are pinching there and kind of connecting these two grain boundaries. Okay. So, this serrated high angle grain boundary will be there will be an impingement here. Okay. And that this will happen when you are approaching 1 to 2 subgrain size. So, this thickness of the or the distance between the two high angle grain boundary is equal to 1 to 2 subgrain size. Okay. That means only maybe one subgrain will be there. Okay. So, and will become comparable with the grain thickness at a strain approaching 5 to 10. So, you can understand that the strain has to be very high to have this kind of recrystallization process. Okay. Very high strain of 5 to 10 you have to impose to get this kind of process. Okay. So, this is what is the schematic mechanism. Okay. You can see that there are some big grains are here, and within them there are some small subgrains are formed. Okay. As you keep deforming, what will happen, this kind of serrations will form in the high angle grain boundary, and within that you can see in some cases one single subgrain is there, in some cases there are two subgrains are there. Okay. Single one, two, and the serration, the wavelength is almost equal to the subgrain size. Okay. So, a very interesting microstructure. Okay. And somewhere you will also see a high angle grain boundary dividing the. So, this is the original one which must have been there. Okay. and below that now you can see that what is the how the spacing between high angle grain boundary is changing. Here there may be almost 10 subgrains were there, now only 1 or 2 subgrain is there, okay. And even if you keep deforming it, what will happen now, these high angle grain boundaries are impinging with each other, and with only 1 or 2 subgrains are there, okay. One here, only 1, in some cases it will be 2, okay, and the pinching off is taking place. So, now this will convert into smaller grains with surrounded by high angle grain boundaries, okay. So, the recrystallization is completed and it is a geometric process, okay, as you can see, a very geometric process, that how it is taking place, that is why it is called geometric dynamic recrystallization. You can see on this curve also, as a function of strain, grain thickness and subgrain size are plotted on the y axis, okay. So, the subgrain size is shown here, okay, which remains almost constant, which is what we see in case of dynamic recovery also, okay. And the grain thickness is changing like this continuously. So, it is very thick initially and then it is coming down and it is getting very close to the subgrain size, okay. And this is the point where it will start showing the that the recrystallization is happening and impingement is happening or pinching off is happening, and you can see the strain is almost between 3 to 4, again very high strain, okay. So, when the subgrain size is equal to the spacing between the high angle grain boundary, okay, then you are reaching that condition of pinching off. There is another one type of dynamic recrystallization which is called meta dynamic recrystallization, okay, a very interesting phenomena. Basically it is not a kind of a as a typical type of dynamic recrystallization. It actually happens because suppose you have suppose a discontinuous dynamic recrystallization is taking place and recrystallized nucleus have already formed at the critical strain, okay. So, when you have this critical nuclei which has formed after the achievement of the critical strain, suppose you have stopped the straining, okay, you are not deforming it anymore, okay. And suppose that the process is like that it is at of course high temperature you are deforming, but you have deformed only up to the slightly above the critical strain and then you have stopped the deformation, okay. You will think that, and if you see the microstructure, you will see a very nice recrystallized microstructure, though you have just exceeded the critical strain. So, in reality it should be only 5 to 10% recrystallized. What will happen that when you are taking it out and if you are not quenching the material immediately, okay, that means it is in hot condition, or if suppose it is in some furnace, it is in annealing condition. So, it is in hot condition after the this achievement of critical strain, okay. Then this nuclei will grow without any incubation period, okay, and you will have a dynamic recrystallization during the deformation, okay. So, sometime it actually happens to capture partial recrystallization, sometime is very difficult, because in some part recrystallization has happened, okay, in some other part where recrystallization is still not started, but during the cooling period when you are cooling the material, and because there is no incubation period, that means it can almost happen instantaneously kind of, okay. So, while you are cooling the material or you are bringing the temperature down, okay, the recrystallization will happen in the remaining unrecrystallized part also, okay, if you have reached the critical strain or exceeded the critical strain. Then it is very difficult to capture that how much is the amount of recrystallized after a particular strain, okay. So, sometimes you have to be careful about this metadynamic recrystallization when you are studying any recrystallization process, that this should not happen during the process, okay. That means the material has to be cooled down immediately, okay, so that you are able to capture the recrystallization process, okay. So, with this this part of the microstructural evolution in terms of recrystallization and recovery process is complete. Okay, and this is one of the very important part, because all the hot deformation processes which we do is to get some very fine grain microstructure, so we can have better property in the material after processing. Okay. So, with that I thank you for this particular lecture.